Yes, please, Professor Munih.
Good afternoon. Good afternoon, ladies and gentlemen. First of all, thank you to organizer to let me speak now, to give a presentation to you, which will not be very theoretical. It will not include many medical things, but it will be more technical. I'm coming from technical background. Speaking about robotics, and in the field of question, what and when will robots enable persons with NMD to walk? Let's start this way. Robots, of course, are today in different fields. We have here on the left side robot manipulators. We have robot vehicles, that's another family, another group. Robot systems that are human-to-robot interaction, and then maybe biologically inspired robots. Today, definitely the field where the robots are influencing our lives is the industry. In the industry, we have many products that are produced and could not be produced without the robots, like mobile phones, cars, etc. Just some shots, some pictures from the robot industry. Another example, which is coming, and it's not yet here parked in front of our house, is the field of mobility. You can already have a very expensive Mercedes S-Class that actually drives itself. You don't have to drive it. It drives on its own, based on the sensors. This is just a short video showing that this is actually not in the research lab, but it's in the field as well. This video is from the internet, and it's showing how this drive is happening here on the highway between Vrhnika and Ljubljana. So the driver is not holding the wheel drive, the car is driving itself, as you can see. Now the next example is even more of that is coming, and the Volvo is preparing bigger technical advances for us. I'll just show you here an example of driving even in the city without the supervising the car with the arms. So this is coming. This is actually almost here. This could almost be bought. Now another area that is also coming is the field of exoskeletons. Exoskeletons are the robots, are the mechanisms that are close to the human exoskeleton. And first of all, I'm mentioning Max Fabiani, which is actually architect. His result is the construction, or let's say architecture, of the old part of Ljubljana that was severely damaged after the earthquake, just before the 1900 year. And he has also a big track outside of Slovenia. But only a few people is aware that he was also an engineer in some sense. He got his patent acknowledged by, at that time, Vienna Patent Office for what we would say today an exoskeleton robot. At that time, he was started to be around 50. His breath was not so long enough to climb the hills, and that's why he started to think about the mechanisms that would help him to do that even more years. And now here we have a table that you don't want to be read, I think. And this table is just showing some examples of the exoskeletons today. Many, many efforts have been put into that area, and there are also some very nice results. Like Honda is investing into that field in different mechanisms. One of those that might be very promising is this here, that is some sort of strange mechanism that allows people to support them to enable walking even if they are not strong enough. One story that's in this field is also coming from Berkeley Robotics, Human Engineering Laboratory, and that's a whole list of the events. In the year 2004, BLIX, that's the Berkeley Lower Extremity Exoskeleton, was formed and designed. That was aimed basically as a research device, but with some thoughts for the military use. Based on that, in year 2005, was developed another exo-hiker. I will show it in a moment. Just before we continue, I will show you a few pictures, slides, or the shots here, showing how big the sensors, the sensory part of that exoskeletons were. This is an example how small the units are today. Also a few words about the control of that device. That device was, let's say, voluntary controlled. Actually, this is equation, the only equation in my presentation today, that has term D. And D is actually something that is stabilizing this mechanism, and D is something that is coming from the person. The person has to add some voluntary activity, and then this stabilizes the whole mechanism. So the mechanism is not positionally controlled from this to this point, but it's rather 100% dependent on the activity of the user. Now there's an example of Hulk. Hulk is actually the Blix mentioned earlier, but that mechanism was obtained, so we missed something here, was obtained by Lockheed Martin Corporation. That's the same corporation which is also making the airplanes. That's why the super materials and super other approaches were used in order to enable the person carrying. You see that the exoskeleton is looks very lightweight, very thin, almost no obstruction to the person, and that person could then carry a heavy weight, up to 100 kilos, which is, I think, in my view, a big achievement. To be short, not to list all the steps, after that, this technology came back to academia or back to research, and here we see EXO, that's basically the same company, which is now, the system is now aimed for paraplegic persons. So for the community, not for the killing somebody. And that's very nice to see. That is now also commercially available. The system is shown here. The control of that system, of course, could not be the same because the paraplegics could not voluntarily add some activity. In this case, the control is via position and through the crutch push buttons that supervise activity. I'll just show you a short video here that shows use of EXO in public. That was filmed, I think, last year. The event in Zurich, and you see the lady here that is walking as a paraplegic person in the community, not in some isolated and intentionally organized environment. So this could also now be, as far as I understand, bought on the market. There are several other, not exactly the same, but similar systems. That one, which is called Indigo, is coming also from America, from the southern part of America. And of course, I'm always interested in what is happening on the other part of the world. Another part of the world in this case would be like Eastern Bloc, Russia. What was happening there in that field? And I could mention that in 1969, Professor Vukobratovic from Mihailo Pupin was actually the first who made a prototype of exoskeleton. And then for some period of time, there was a hole. And exoathlete is something that was today developed in Russia. Looks quite good, I would say. These are just initial shots. But all this shows that the field is developing, not only in some isolated point, but also widely, and that the interest is wide. And of course, this is then also good environment to have some real results. Not to be too long, I will just continue. Another example of similar mechanism is coming from Israel. It's called Rewalk, and the achievements or the function looks to be very nice. Rewalk, as you can see, allows somebody to walk outside, and the use seems to be very independent. Again, the lady is paraplegic. The control of this is through the crutches, through the push buttons as well. And of course, the system is following whatever the commander, that's the person, is trying to trigger. Next system would be REX. REX is, as you will see now in the video, I will show you the video, and you will see that the REX is a big device, a very powerful device that also takes care in a great deal for stability of the person. It looks very bulky, but from some point of view, this means that the person does not have to do anything. Actually, the system is doing everything. Of course, the moving big masses could not be very fast, is slower, and to maintain stability, of course, there is more or less issue of static so-called stability. There's no dynamic stability which we usually use in the walking or some other activities. Another example that is coming from France, French cobot. So far I didn't use the word cobot. It could be co-worker or something, some mechanism that is helping to the person. There's a whole area of cobots. The cobot would be, for instance, a simple device that would empower, that would increase the power of my arms. And that could be the simple mechanism used in post office to lift off the bags or something heavy. I would add like 5 kilos and the system would produce the force of another 50 kilos. And in this manner is designed this French system that is, of course, planned and used for the French army. As far as I understand, it was also tested in Swiss army. The interesting thing is that, of course, there is an exoskeleton. There is also connection with the arms. That was not seen in the other systems before. This is available on the internet commercially, but I don't think that you can buy one at the moment. Another system coming from Japan is HAL. HAL is very interesting regarding the control. Initially, it used surface EMG electrodes. All the previous systems were not controlled in this manner. The previous systems, as maybe you noticed, and I specifically mentioned that, they were controlled by measuring the interaction between the human and the exoskeleton. In this case, the surface EMG electrodes are measuring muscle activities. And then, of course, these pictures should be familiar to you. We measure whatever is coming from the central, from the brain, down to the periphery, and then the system, the robot, is amplifying the movement. For the time, it showed that this kind of control is not very reliable. Of course, there are cases where this could work. This control was not very reliable. That's why this control was somehow modified, shifted to the same approach as we saw it before through measuring the moments and the loads on the system. Now I would like to show you some examples that are coming, let's say that we are involved into the work of those exoskeletons. And one of the research activities of our group was also in the field of Embryon project. This Embryon was characteristic for a very much different design of the system. All the masses were more or less composed and put here close to the hip joints, which means that it's very, in terms of movement, very lightweight. The user feels almost anything. It does not feel any heavy weight on the segments. And that was the very big plus for this system. This was also for us entrance into the field. As you will see now in the next slides, we were trying to measure what the person is doing. What is the person trying to do? Because the next project, which we got it more or less with the same consortium, the Italians, Santa Ana, then the UCL, that's the Belgium part, then the VUB, Brussels, University of Ljubljana, and also some other partners. We are working on orthoprosthesis. On one side is prosthetic addition or substitution, and then some help on the other side, we presume that this person is not able to move without that help. And of course, this is really help. The video that you will see now is actually live video of our results. The user, Mr. Bellini, is amputee, walks outside. Of course, there are some engineers walking with him as a demo side, but as you can see, the walking looks very natural, I would say. So the system is offering not limitation, but help to the user. Speaking about our activities in this area, we are those which we are measuring the activity, and we are trying to say what will be next, what will be happening next. And all the pool of activities could be organized in such a way. Of course, we have to stand up, and when we are standing up, we have to start to do something, either stair ascent, walking, or stair descent. And then when we do something, we have to terminate, and we can again sit down. All of those phases could be subdivided into different phases. You know, the walking is usually double stance, and then the other phases. And also standing, also the walking up the stairs, or walking down the stairs, descend. And also when you stand up and when you sit down, everything is nicely divided and everything could be nicely measured. For this purpose, we use very simple wireless inertial measurement units that are, let's say, small circuits that are positioned, that are placed on different parts of the body, and then from some small movements, we recognize what the person will do, what the person is trying to do. Some of the systems that I showed you today could be bought. Some of the systems that I showed you today could be rented. Our aim is, in some sense, to have very cheap system to enable people not just these activities, but maybe some activities that are not mentioned in this talk. So again, when will robots enable persons with NMD to walk? I could say I don't know. But I definitely know that the robots are helping, and they are very convenient to help maybe very much to the group of NMD in the other fields of the robots, like the example that I showed at the beginning in the field of driving. Or, I don't want to go into another area of robotics, in the field of robots for upper extremity, for assistance, for support. These systems are already available today, and they do offer, I think, very nice and very competent help to the human. At the end, I have to mention, I have to thank all the supporters of our work through different projects, and of course to my co-workers. If there are any questions, please.